Hi, my name is Hussein Osman. I'm super excited to be presenting today at the Lattice Developer Conference. I really enjoy FPGAs and ultra low power FPGAs, so my intent for this presentation is to give you a little bit of view into what type of applications and solutions ultra low power FPGAs solve in the consumer market. So let's dive into it. Just a little bit about myself. As I said, I'm really a fan of FPGAs. I've been with Lattice Semiconductor for about 6 years. I focus on the consumer market and the client computing market. I also lead our SenseI solution stack. I've worked with FPGAs over the past 15, 20 years, working as a system engineer and then as a marketing leader within Lattice Semiconductor, I got to dive deeper into the capabilities of FPGAs and all the applications that are possible with ultra low power FPGAs. So moving on to what the agenda for today is. So I will take a step back and talk a little bit about the basics of FPGAs, what makes up an FPGA, what's inside the fabric, what's inside the package you get as a FPGA user. What are advantages of FPGAs over other devices, and what applications do we see frequently use FPGAs, especially on the consumer market and consumer devices, and a deeper dive on that in terms of use cases, interfaces, what devices surround the FPGA normally, and we'll close by some more specific information on Lattice and products that enable the applications we discuss throughout the presentation. So moving on into the presentation. So the basics of FPGAs, if you want to think of an FPGA, it is basically a fabric of connectivities, wires that are crisscrossing throughout the device. That's the first block on the left-hand side. And then to the right of it, there are some SRAM blocks. These are memories that are very close to compute. Also, there are clocks, PLLs, and clock managers that enable uh, the clocking of the logic resources. The smallest logic resources on an FPGA is called a LUT, a lookup table, and it's basically a multi-input logic that can be defined, and based on the definition, an output would be taken out of the design. So in addition to SRAM, you see that there is DSP multipliers normally. Those are the purple things on the bottom left diagram. And then possibly a processor or some hardened I/O blocks like I2C, SPI, UART, USB, and so on. By design, FPGAs provide a massive parallel compute capabilities, enabling the connectivity of multiple LUTs together and ability to run them simultaneously. You find FPGAs used in video processing applications. You find FPGAs used in glue logic, motor control, AI, and other communication devices. In terms of a design flow, it's a bit different from using an MCU. A user would have to input an RTL or a description of the hardware into a synthesis tool. This RTL should be simulated and made sure that it is accurate and it does the function it's supposed to do. Information about the FPGA type, pin assignment to pin out the design, and constraint for timing for any path will get entered into the synthesis tool as well. And those are taken into an FPGA design tool after synthesis to place and route and then output a bit stream that is normally stored in external memory next to the FPGA or behind a CPU or MCU that boots up the FPGA in the beginning of the design. So now you have a basic sense for how to design an FPGA. design or implement an FPGA design and deploy it on a device or a system. Thinking about FPGAs and advantages of FPGAs, as you saw, there's certainly a level of programmability that's possible with FPGAs. Each one of those LUTs and DSP resources and memory can be tied together through a design. Normally, you do see a boost of performance versus using serial execution engines like CPUs. Normally, FPGAs are readily available in different sizes, different densities, I/O capabilities, so it reduces the time to market. Um, and there's a certain level of longevity that's associated with it, flexibility of I/Os and deterministic. We'll dive deeper into each one of those. So on the programmability side, if the design needs to continue to adapt to changes and adding new hardware, then an FPGA is a really good solution. Also, if there are interfaces in the system that are evolving or changing, or the algorithm itself could change, and the designer wants to delight the end user by providing over the air updates, that plays favorably in an FPGA perspective. Um, any new regulations, any new changes that are envisioned to the system will come also under the programmability or the advantage of the FPGA in terms of programmability. FPGA life cycles are normally 10 to 15 years versus ASICs that are 5, 7 years maximum. So if the product is to stay on the shelf for a long time or stay with users for a long time, having an FPGA is an advantage. Boost of performance. FPGAs can help boost performance, and you see that especially on heavier loads like video processing. Um, Normally, if you do this on a CPU, you get a serial execution and a heavy workload that's on the CPU. FPGAs normally come in to offload some of these heavier workloads into smaller devices that are lower power, um, and you can create a user designer can create a fairly tailored solution for how to create the design. And lower power is normally associated with the fact that the FPGA runs at a lower clock speed and running things in parallel. IOs in an FPGA are some of the most flexible in logic devices. So there's normally a set of I/O choices that are available in an ASIC. In an FPGA, you get a generally programmable FPGA. Virtually can support any type of FPGA. Virtually, you can choose from different packages and I/O types to support any quantities of I/Os. Also, that provides the ability to create a set of custom peripherals. So programmability, performance, I/O expansion, longevity, and reduce time to market. So we see a lot of times system designers have an FPGA, a small FPGA that's in the system sometimes to allow prototyping, adding new ideas, and continuing to be a market leader by delivering those ideas fast to market. Um, Final point here in terms of FPGA advantages, I would say that is the determinism of the design. It's by hardware design, you can create logic that is deterministic. You know exactly when the input comes, how long it will take to get an output. That's a little bit different from a system that has interrupts and a CPU software cycle that can be busy doing some other things versus a hardware deterministic solution such as an FPGA. Um, Moving on to consumer applications. Normally you would hear that FPGAs are these larger devices, power hungry, that are used for prototyping only. But over the past few years, I've seen basically designs for FPGAs that are all over different applications. Sound bars, audio applications, streaming media boxes. These are normally IO related applications. HMDs, headsets, and AR, VR sets. You see there are many cameras on those devices, and they need to go to an SoC. Home appliances such as display driving, a home assistant devices and audio bridging, headphones, also audio improvement and audio conversion. So FPGAs are not used only on communication system or servers. They're actually heavily used in consumer applications to create new ideas and take them to market quickly to solve some IO mismatch or standard mismatch issues that arise. So I touched a little bit on this, but to just summarize, these are the three areas that are the most popular use cases for FPGAs. IO bridging, just different standards that are needs to be connected, glue logic, having to create some custom logic that interfaces to subsystems, for example, and high performance processing, such as video and audio processing and AI. Digging deeper a little bit into the connectivity and the glue logic, provided here are four common applications for consumer devices to implement on an FPGA. So processors on the left-hand corner and sensor buffering, processors that have limited number of IOs can expand its IOs through a USB or a SPI port with a custom number of peripherals on the other side. I'm showing multiple SPIs and multiple I2Cs and a GPIO. Those are totally can be configurable for different interfaces. And also there could be some special arbitration logic, time stamping or sampling that's ongoing. This allows for the processor to either stay asleep longer or take care of other tasks while the logic within a device such as the ICE40 Ultra Plus from Lattice can arbitrate and manage the data from sensors and only interrupt and provide information to the processor when needed. On the top right corner is a MIPI aggregation example. In this example, it's an AR VR headset where there are multiple sensors. Some of them are world facing, some of them are user facing, and those sensors all need to go to the AP or CPU. And an FPGA like Crosslink NX has multiple CSI inputs. I think up to 10, 11 inputs are possible depending on the resolution and the frame rate. So all of this can be aggregated, mux switched over to the AP. On a bottom left corner is a MIPI to USB full camera pipeline on a device such as the Crosslink NX. This enables connecting to different type of sensor. If the designer within one product has multiple sensors to support, this way you can connect these different sensors to a processor through USB. An ISP pipeline can be implemented. And I have a full session on this topic you can look out for USB and ISP ultra low power implementations. So it's part of the conference and you can look for that track. On the bottom right hand side is a example of this time going from a processor to multiple displays, and display splitting is something that can be done given that there are multiple high-speed MIPI transceivers that are available in some of the FPGA devices, and Crosslink NX is an example of that. So I want to highlight one more application, going a little bit deeper into this application. This is called single wire aggregation. And we see a lot of times in systems, there are challenges related to passing signals from one part of the system to another part of the system. These signals can be, there's limited space for them to pass through, or they're moving parts that do not allow many wires to be passed through. And just highlighting the flexibility of an IO on an FPGA, an aggregation solution can take a number of interfaces through a single small FPGA, aggregate them over a fast serial interface, and then take them to another part of the system and kind of break those out to the same interfaces. The key for using an FPGA here is latency and software support. So the latency, typical latency for those type of applications on an FPGA, we're talking about less than 1 millisecond. So from a system perspective and the speed of these interfaces, that's negligible. Also, being able to just have all sort of interfaces that can be aggregated over these fast speed serial interface helps a lot. Moving on to processing, and on the processing side, we see AI processing as something that FPGA handle very well, especially the low power side of things. So in this example, if you have a robot that's battery powered, running on the edge, wants to collect information about who's in front of it and not hit somebody, wants to track if there is any objects that are in the ground. An FPGA such as the Crosslink NX is able to interface to image sensor, implement a an AI pipeline, and then implement an ISP as well, and be able to feed to the processor the video and some metadata on top of that. In the right hand side is an application of, again, an image sensing processing, offloading a processor of the ISP pipeline, interfacing to the image sensor, processing images, providing good quality images. And there are some specific advantages to FPGAs with video processing. And again, take a look into my session on this topic. Many FPGA vendors kind of provide, along with FPGAs, a set of software solutions and IPs that enable getting to market quickly and enable designers who don't want to spend too much time digging into each block with IPs and reference designs that give a general good starting point. And at Lattice, we have a few solution stacks: SenseAI, Envision, Sentry, and Automate and ORAN. So on the consumer side, we see a lot of the SenseAI and Envision. So we'll dig deeper into those a little bit. So on the Envision, the ISP pipeline is a typical application for what we call Envision solution, sensor fusion, aggregation splitting, lighting, and just general co-processing of vision pipeline within the processor. On the AI, things like human presence detection, identification of intruder, gesture tracking, multiple use cases that are possible with SenseAI. The trends that we are seeing here is there is a significant movement of compute from the server to the edge devices. And again, that's driven by things like latency, privacy, security concerns that users have, bandwidth limitation, number of cameras that are always running and uploading information to the cloud. So it's better for the user to have that compute, or a significant part of that compute happen local within the edge device. And the choices of edge processors have been increasing, and they're very capable. They're just as capable as the cloud servers, and they're efficient in terms of their computation and power consumption. These are all drivers of having that compute move from the cloud into the local device. FPGAs tend to do really well for edge compute due to the following: the ultra low power capabilities of the device, again, parallel compute, lower clock rates, and ability to run things sequential in parallel provides overall lower power consumption for the same use case versus an MCU or some ASIC capability, some ASIC devices. The flexibility of the resources, having to create a AI accelerator, an ISP, some other functions, it's really useful for a system designer to have a device that is able to do multiple things at the same time. Scalability of performance and handle multiple use cases. In a lot of applications, what we see is an FPGA would run the AI processing inline. It's not storing anything into memory. It makes it really easy to context switch between use cases and enable multiple use cases at the same time. Security of data, FPGAs tend to have secure block for authentication of their firmware and sometimes for even securing the data in flight. And hardware programmability. The AI acceleration engines are normally made out of resources of the FPGA that are tied together. They're not made out of a hardened engine. And so as the AI models evolve, the accelerator engine can be optimized and changed to keep up with the changing world of AI models. Some, example applications that can always can all be supported through an FPGA. So, from Lattice's perspective, some devices like the Ultra Plus can do simple object detection. These are binary classifiers, vibration, key phrase. The next generation up of devices in terms of performance are the Crosslink family, and the Crosslink NX is able to do multiple object detection, user identification, scene classification, and segmentation. As you go up the throughput and requirements need, there are also larger devices like the Certus Pro NX and Avant. They can solve user identification use cases, multiple video stream analysis for cameras. As the performance and the throughput requirements needed, there's normally an offering of devices, and Lattice has an offering of devices that's able to support these use cases. This is our Lattice SenseAI stack. As I said, in order to enable easy implementation of AI use cases, vendors, including Lattice, provide a set of tools. These can be hardware platforms like the ones all the way in the bottom of this diagram. Then you have some accelerator engines that are specifically created for different devices, tools and software like compilers and training tool and FPGA tools, demos and reference design that cover different use cases, and then some design services or partner ecosystem to enable the deployment of use cases within FPGAs. Before I kind of go to the next step there, for a resource, if you go to lattice.com, applications, you click on SenseAI, there's a really useful page that goes into the details of what's all the pieces that are available from Lattice to enable edge AI deployment. On top of that, Lattice has worked on creating full end-to-end solutions. So this is another way. If you're looking for a person detection or a person tracking solution, there's already an end-to-end solution that's available. And if you have additional questions about that, you can reach out to me. But those are type of things that can be supported, like presence detection, depth sensing, gesture, hand, body tracking, face identification, human skeleton track, and object detection in general. We tried to create a set of useful AI applications. These are production ready applications and can be deployed on Lattice's FPGAs. This slide just goes a little bit deeper into the use cases. So the attention sensing includes face position, where is the user exactly in the field of view XYZ, their head orientation, pitch, yawn, roll, facial landmark, are they speaking, are they quiet, multi-user detection, how many users and where are they exactly, where is their gaze focused. So many applications that are possible with the FPGA are highlighted here, and kind of we have the pieces to enable those in a customer system. So for additional information, please reach out to me and we can discuss this in more details. Um, so we covered right now how AI can be deployed on an FPGA. Let's move a little bit into vision and some of the vision trends that are out there. Most systems now, or quite a bit of system, have multiple sensors. These sensors are higher resolution, higher frame rate. Oh, there's a massive deployment of this great quality sensors. There are interfaces like MIPI that keeps on changing, and there are legacy component and other FPGAs, and we touched a little bit on the FPGA process, on the AI processing piece of it. So in order to kind of support the designs that are needed to meet these trends, you need a low power, a video subsystem processing. Most times, small form factor is a requirement. The performance needs to meet the speeds and feeds that are required for the system. Reliability for that to continue to work under harsh conditions or thermally challenging conditions. And this needs to be easy to use. It can't be complicated to put together a system for embedded vision. And Lattice provides a solution very similar to SenseAI, includes kits, IP cores, software tools, reference design, and custom design capabilities to service these applications. For example, on the IP core side, you get ISP pipeline, and we'll talk about that on a separate session in more detail. Sensor aggregation, sensor bridging are some of the typical consumer applications that we talked about previously, and there's demos that shows how to put those together. Also hardware platforms for different devices to enable this capability. All right, so just to give you more view into IP cores that are available from Lattice, if you look at the image processing, for example, you see your typical building block pieces that are needed to build an ISP are supported. Also on the bridging side, receiver, transmitter for CSI and DSI, ability to do byte to pixel conversion, pixel to byte conversion, and different MIPI to PCIe, MIPI to USB, those type of building blocks are available. Finally, kind of touching on what is the offering from Lattice to enable these use cases. So that from an FPGA perspective, Lattice has some very special FPGAs, video connectivity on the bottom right left corner. These devices are fairly small with hardened MIPI D5s that enable processing or connectivity into image sensors and bringing those image sensors into the system. We can run some additional processing within the system, like an ISP. The connectivity of video, these devices are perfect for that. On the I/O expansion and the glue logic, the ICE40 Ultra Plus on the bottom middle are perfect devices for that. Those devices typically have microamps of power consumption, static power current consumption, and they're as small as 1.4 by 1.4, so they can fit into very tight spaces with a good quality IOs to bring in data and send data out. On the top, these are general purpose FPGAs. These FPGAs tend to have more capabilities, like 10 gig SerDes, up to 150K LUTs. The ICE, for example, the largest device is about 8K LUT. The Crosslink family, the largest device is about 40K LUT. So the devices on the broad family are used for heavier processing. For example, video processing on a projector system for consumer use would require some ability to bring in the video and do some things like keystone correction or just improve the quality of the video as it goes to the projector. So this gives you a good feel for what Lattice has to offer in terms of devices. Um, and really, Lattice's value proposition has been around building programmable, small size devices. You can see the device in the middle of this picture, small as a salt piece, and power is in the middle of this. Our devices are 4 input LED devices that are optimized in by process, by architecture to meet the lowest power needs of the designer, security authentication blocks that are dropped in, the tools, software tools, and solution stacks to enable reliable design, building, and just an ease of use overall. So this kind of brings me to the end of the presentation. In this presentation, you got a look into how FPGAs can be used to create low power consumer applications. This is driven by the flexible IOs these FPGAs have, the programmable and future-proof logic resources that can enable many applications today and in the future. The parallel compute of the FPGA enables vision and AI and edge AI application. Lattice overall has been focused on ultra low power FPGAs optimized in size. This ICE 40 Ultra Plus, for example, is a great device for consumer application. And then you see a number of off-the-shelf solution and IPs to enable system designer to go quickly through the design and get to market. With this said, this is the end of my presentation. I will now transition to taking some of the questions you might have in this area. And so I see some questions are already rolling in here. First question that I see is, what is the difference between a 4 input and a 6 input LUT and advantages to each? So yeah, we didn't touch too much on that, but a LUT has a predefined number of inputs, and that's the basic part of the design of the FPGA is a LUT. A 4 input LUT is a logic resources that has 4 input on which you can design logic, and the output will be determined based on the input. A 6 input LUT is just, instead of 4, you have 6. And Lattice really focuses on the 4 input LUT, and those FPGAs tend to be lower power consumption, and they tend to be smaller in size in general. For many designs, a 4 input LUT is more than perfect enough. For some higher performance application, you could, or you might need to have a more complex 6 input LUT. This would in turn drive better performance, but also would require higher power consumption to achieve the performance needs. The next question that I see here is when to use an MCU versus when to use a small FPGA. So that's a pretty good question. MCUs are everywhere. They're used for many applications. So how do you decide whether to use an MCU or an FPGA for an application? And I would say that it depends on the workload. If the workload is heavy enough and an MCU would have to stay on the entire time running at full frequency to achieve the workload, it's going to be higher power consumption. And probably that workload is better tuned for an FPGA implementation, especially if it's a video processing or something like that. If the application has lots of time where there is little processing, an MCU, especially for a power and a battery powered application, an MCU will tend to be a better fit for that because the MCU static sleep current could be in the micro amp range, while the FPGA static sleep current could be somewhere, while program in closer to 1 milliwatt range. So it's all about the balance of power and performance that's required that drive the choices between an MCU and an FPGA. I'll do a few more questions here. The next question is provide an example product that benefit from always on AI applications. So, cameras or doorbells are a good a good place to implement always on applications. Uh, First generations of webcams or doorbells sent all the information to the cloud, and it allowed the cloud server will send a notification to the user presence of somebody in front of your house or something like that. And so um, having a, a on device compute, a small gear that kind of processes the information and decides, is this really a person or is that just a dog that's moving around, before sending the data to the cloud for further processing and analysis and a notification to the user. This improves the user experience. It improves power consumption, security, privacy of our data, as less data will get transmitted to the cloud. Um, the next question is, FPGAs could be tougher to use, harder to use than MCUs or ASICs. What are the tools that enables deployment of applications within FPGAs? So I touched on that quite a bit through the presentation. There are at Lattice, we provide the FPGA. We provide software solutions on top of the FPGA to enable the ability to put the design together as fast as possible. And then we provide as well reference designs and demos. In many cases, these demos, reference design can be taken as is and moved into design. Of course, you need a little bit of RTL capabilities to understand how to stitch things together. There are also a number of tools out there, like a high-level synthesis tool and design capability that allow for deployment of applications without deeper knowledge of the underlying architecture of the FPGA. At Lattice, we have Propel. It's a tool that allows the grab and pick and drop of different IPs together and stitching them in a graphical interface to allow for system design. So there's over the past decade or so, the use of FPGAs and the ease of use of FPGAs has been improved significantly. The next question is why run an ISP on an FPGA versus on a CPU or SoC? So I would say latency, power are the main drivers for that. Ability to customize the actual ISP would be third in my list. You can drive extremely low power with an FPGA for that use case of an ISP. So latency for FPGA have specific numbers here, about 10 millisecond latency on processing of a 1080p 60 type of image sensor and running full ISP with that. Everything is running in line. There is no need to go off to an external memory unless an entire frame needs to be kept. But for many application, not including 3D noise reduction, you can process the entire frame without some external memory needs. So there is advantages to kind of offloading an SoC or CPU with a ISP capabilities on FPGA. I think we have a little bit more time, so let me take one more question. What type of I/O are generally supported by FPGAs? Many types of I/Os are supported. Your typical low-speed I2C, GPIO, UART, I2S, but higher speed serial interfaces like PCIe or USB are also supported within an FPGAs. Other serial interfaces such as MIPI, CSI, MIPI, DSI are also common within FPGAs. Okay, so if you have additional questions, feel free to submit those questions and I'll receive all your questions and I'll go through them and reply and we'll get back to you with some answers. It's been a pleasure to kind of walk you through all the typical FPGA applications for the consumer market and how FPGAs can drive ultra low power implementations. If you have further questions, please shoot me an email, hussein.osman@latticesemi.com. Glad to talk to you today and thank you for your time.